Okay, here we will return to the Springhill suit at the Newark International Airport, Springhill Marriott, and we're demonstrating Kirchhoff current law. And suppose now we have all right, suppose we have the diagram and let's just arbitrarily now we're going to assign some value. This is resistance, say 1. Let's start off here and call this 1. And this is 2. This is 3. This is resistance 4, resistance 5, resistance 6, resistance R7, and R8. And suppose if we assume now that with I1, R1, resistance I1, it is a current I1. And let's just assume now that it is going in this direction. It's going into this node joint here. Okay. And for R2, we say, let's assume it's also going in. And let's assume that R3 is moving out of the node. R4 is moving out. R5 is going in. This is our assumption now. And R6 is going in, and R7 is going out. And R8 is going out. All right, so Kirchhoff current law now, KCL we're going to call it, KCL, standing for Kirchhoff current law, said that the sum of the current entering the node must be equal to the sum of the current leaving the node, or that the summation of the current at a node would be equal to 0. So algebraically now, if we say now that R1, we're going to assume a notation that in is positive, in equals plus VE, and out as minus VE or negative. That is our assumption of the direction. We could have a reverse assumption here, but this is the normal assumption that in is positive and out is negative. So we don't say that according to the Kirchhoff current law, we'll have know that I1 in, which is positive, I1, this would be I2 now, a corresponding current I2 is going in, plus I2 going in, and this would be I3 is going out, so we see minus I3, and R4 is going out, a current I4 out minus I4, and R5 we assume it was going in, plus I5 going in, this would be I5, and R6 we also assume was going in, so plus I6, I7 was going out, minus I7, and R8 was going out, minus I8. the sum of the current at a node must be equal to 0. Therefore, we say now that I1 plus I2 minus I3 minus I4 plus I5 minus I6 minus I7 minus I8 must be equal to 0. That is Kirchhoff's current law applied. Or otherwise know that the summation of the current now which is this I1 minus I2 minus I3 minus I4 plus I5 minus I6 4, 5, 6 was going in, so with plus I6, 7 was going out, and 8 was going out. Sum of the total, we call it I total, at a node must be equal to 0. So we could put here summation of I equals 0. Or otherwise we could say no, the in must be equal to the out. So in, the current in would be I1 in plus I2 out. So we'll leave the house. In would be this one is for this one, this one is for this one, and this one is for this one. I5 in is also I6 must be equal to the outs. All these are in, must be equal now to out would be I3, out is I4, out is I7, and out is I8. So the ins equal to the out. I1, I2, I5, I6 are in, and I3, I4, I7, and I8 are out. So that's another way of putting it. So if we assign some value now to I1 and R1, then we could find some unknown. So suppose if we make, say, I7 is unknown, and we wish to find I7, and we assume some values for the resistance R1 and I1. Let's arbitrarily assign now that resistance 1 is equal to 1 ohms. Resistance 2 is equal to 2 ohms. Arbitrarily, resistance 3, for simplicity, equals 3 ohms. Resistance 4 equals 4 ohms. Resistance 5 equals 5 ohms. Resistance 6 equals 6 ohms. Resistance 7 equals 7. And resistance 8 equals 8. Now, in normal life, we're not going to have these resistance 1 equals 1 ohm, resistance 2 equals 2 ohms. It might be resistance 1 equals 5 ohms, resistance 2 equals 4 ohms, resistance 3 equals 7 ohms. But I'm just assuming it like that. So we could go ahead and substitute these values now and find the voltage drop at each resistance. So for the voltage drop across here now, it would be V1 would be equal to I1 R1, and that would be equals now to I. So let's also assume arbitrarily now that I1 was, say, for simplicity, 1 amp. And for simplicity too, let's assume that this a uniform current was going through, for simplicity. So that I1 is equal to I2 is equal to I3 is equal to I4 is equal to I5. All equals to unity. But the resistances are different. So don't think that now V1 would be equal to I1 R1, and that would be equals now to 1 times 1 would be equals to 1 volts. And V2 would be equals to 1 because I2 is equal to 1 times 2 would be equals to 2 volts. So our assumption is now that I1 equals I2 equals to I3 to I8 equals 1 amps. That is our assumption. I1, current flowing to I1 is equal to current flowing to I2 equal to current flowing to I3 to I8 and is equal to 1 amp. This just to simplify our calculations here. So that now V2 will be equal to 2 volts, V3 will be equal to I1 R3 will be equal to 3 volts, and V4 will be equal to I1 R4 be equal to 4 volts, and so on. If R2 at a different value, say for example, all right, if I2 at a different value, we would have to know that I2, suppose I2 was equal to say 3 amps. Suppose. Then what we'll have for I3, I2 is equal to 3 amps. Then the voltage drop across R2 now would say that V2 will be equals now to I2 R2, which will be equal to 3 multiplied by R2 is what? 2 ohms, and that will be equal to 6 volts. We're now assuming that each has a different current. And suppose, likewise, that I3 was equal to, say, 5 amps. Then the voltage in across now the R3 would be V3 is equal now to I3 R3 is equal now to 5 multiplied by R3 3 is equal to 15 volts. And arbitrarily now, let us assume, say, V8, that I8 was equal to, say, now 4 amps. What you'll have now is that V8 would be equal now to I8 R8, and that will be equal now to 4, and R8 was equal to 8 multiplied by 8 equals to 32 volts. You can also make some other assumption, we take anyone, say R4, I4, So assume that was equal now to 2 arms. So that now the V4 equals to I4, R4, and that's equal now to 2 multiplied by R4 was equal to 4 equals to 8 volts. Now if we're taking in consideration the polarity now, current going so this would be plus minus. Plus minus. This would be plus minus. Our current flow from positive to negative. So the resistance is the way it would be taking on. It wouldn't have any sign, but the current and the voltage, they could take on negative and positive, depending on the direction of the flow. But if you calculate and you assume it is going in one direction and you get a negative value, that means it was going in the opposite direction. That's how you interpret it. If you assume that the current was going so, and after you make your calculation, you get a negative, then it means that the current was really flowing in the opposite direction. So that is a demonstration of Kirchhoff's current law, that the sum of the voltage at a node must be equal to 0. And we algebraically expressed it. The voltage, the sum of the current at a node must be equal to 0. Which alternatively, we put it that the sum of the in current must be equal to the sum of the out current. So that's another way of putting it. And this was just some arbitrary assignment. You could go on and exercise your mind in this, but make sure when you apply the law here now, you take in consideration the direction of the flow of the current. And if you assume a direction is in one way and you work it out and you get a negative, that means it was going in the opposite direction. So that's a simplified demonstration of Kirchhoff's current law according to this diagram. All right, next I want to do a mesh analysis. If we have the time, we'll come back and do a mesh analysis. Which would be now, let me just draw up the mesh here, like taking so, suppose if we have now, we call this mesh 1 and this mesh 2. And we say this is say A, B, C, D, and say if we call this now E and F. So for one node, it would be A, B, C, D, and for node 2, it could be D, C. So this is going so, the current will be so. So we're gonna, after a break, we're gonna come back and try to solve this circuitry via a mesh analysis. And we'll assume now that this resistance here will be R1 and assign some value. This will be R2, assign some value, R3, and R4. So after break, we'll come back and we'll do the mesh analysis by using Kirchhoff current law, voltage law, and Ohm's law.